Rotary engine side port development through the years. I used to do engine development for a performance speed shop specialising in airflow, hence why I have an interest in the passages feeding an engine. We mainly did old piston engines with poor port designs, so you were practically redesigning the whole top end to more modern practices. This is going to be more a simplified overview than any direct details, and it's really only going to be about normally aspirated engines. I like the precision required with limited resources of normally aspirated. It's like working at the limits of the laws of physics, whereas forced induction doesn't have to be perfect internally. A brief history of the rotary engine. Back in the very early days, the rotary engine had a slight technical advantage with airflow, but then the piston guys worked out how to use a flow bench and actually passed the rotary engine in flow. And on top of that, they worked out velocity and made the port even more efficient. The first advantage was there was no valves to hinder airflow. We'll see later there are other considerations besides a valve obstruction. The second advantage was there was two ports feeding one chamber. It was an advantage in the two-valve piston era, but not so much in the four-valve era. In factory normally aspirated engines, these ports are usually staged. Basically the engine would run on the primary port and the secondary would switch in at a higher RPM. And if you had a 6-port, there would be a third port that would switch in at an even higher RPM. They use a rotating tube on the third port to progressively open it. This is to keep port velocity high, because the higher the velocity, the stronger the pulse strength for wave tuning. And advantage 3 is you have 270 degrees from top dead center to bottom dead center to fill a chamber. Basically the extra 90 crank degrees gives more time to fill a chamber at high RPM. Now some simplified theory. An engine without ports cannot achieve a volumetric efficiency greater than 100%. That is, if you remove the cylinder head for the intake stroke, bolted it back on for compression, ignition and expansion, took it off again for exhaust, and did that 9,000 times per minute, you can't achieve a VE greater than 100%. Now if you added ports and manifolds, which are more restrictive, you can achieve VEs approaching 130%. And that shows how important the ducting is, specifically their dimensions and shape. Basically the top end of the motor makes all the power, and it's the ports and manifolds that are critical. To emphasize this, ProStock will use a short rod with a bad rod ratio so they can shorten the deck height of a block and line up the manifold to the port better, because airflow can make more horsepower than any rod ratio can. Basically, ports and manifolds have the highest order of importance in making power, because it's the major system that puts mass in the cylinder and byproducts out. To understand rotary ports, we have to look at piston ports, because that's the only place where this information is available. First we'll have a quick look at the evolution of piston ports. Back in the old days, most production stuff was on the small side. There were small valves, small ports, sharp turns and low port height, which gave poor short side radiuses. The short side radius is the most critical area in porting, because if it was bad, no air would flow through this half of the valve. When you're putting a single barrel, single carb on everything to save money, ports didn't seem that important. They even used to Siamese ports to save money, i.e. a 2-runner manifold is cheaper than a 4-runner one. Back in those days, bigger was always better. Even with 2 valves per cylinder, this normally aspirated 27-litre Rolls-Royce media tank engine was probably airflow limited by small ports. The aircraft engines were forced induction, and that kind of masks a poor port. Basically there's more pressure differential across the valve, so it can put more air into the cylinder earlier. Later Merlin engines, they joined the 2 ports together to make one big area, because big is safe with forced induction if you're looking for peak power. You can kind of see the low port height and bad turn here. Next we have early American iron, and the ports started getting bigger and the turns better. They're kind of characterized by this drop floor entrance and higher port floor for better turn. These low floor entrances weren't great, because at low RPM there'd be a low velocity profile over here, and at high flow demands the air would ski jump to the far side. You can kind of see it here in real life. You can see EMC winner John Case and his modifications to fix these ports. Ford actually went too far in port size with their Cleveland 4V cylinder heads. We have to actually fill them with blocks to make power. Their exhaust ports were too big also, i.e. too flared on the exit, and turned too severely. This is the original floor of the port, and this is our new smaller raised port. Next is modern aftermarket 2-valve cylinder heads. With these they raised the height of the floor so they could get a better radius in here and allow the air to turn. They lifted the floor at the entrance to get rid of that dead area around here, and they ballooned out the bowl here so the air can slow down and do the turn a bit better. They even started looking at chambers to aid airflow. This is roughly what they're like. Next is Pro Stock. Here they're raising the runner so there'll be less loss in the turn, and they go to a high RPM chamber to aid airflow. Side note, when you buy these cylinder heads, this is what you get, just a blank casting, and you've got to machine everything into it, and that allows you to put everything where you want it to be. Like you might move your rockers and push rods over so you can get a better angle with the port. And lastly we come to Formula 1 multi-valve ports. Here they make the port as vertical as possible and try to get rid of the turn losses. Your street multi-valve heads won't have ports that high. The ports in the Duggan heads we used to do are very vertical. Aries Piston in the US stole this design and sold it off to Fontana for their Speedway engines. Now let's look at a highly optimized port, and that's a 2-valve Pro Stock port. 4 valves can sustain a higher port velocity because they're straighter, more direct port, but with an abundance of valve area, relatively low valve lift, and a chamber that cannot optimize airflow, that area can't be optimized as much. So we'll use a 2-valve Pro Stock port because it's more advanced. As you can see, the inlet passage from trumpet entrance to chamber exit is treated as one unit. The most influential part of a port is the smallest part of the port. This is called the critical cross-section, or the minimum port area, or the choke window, and it's located at the throat just before the valve seat. And it's this area, or more importantly the velocity at this point, that dominates everything else in shaping the power curve. Just as cam duration sets the RPM range of a cam, this area sets the RPM range of the whole engine. Basically, if the area is not correct for the RPM you want to use, this engine will never perform properly. The whole crux of competition engines is to tune all the systems for 1 RPM, so that their powers stack on top of each other. If you mismatch all the system's RPMs, you can make a very flat power curve, which is very versatile and foolproof, but this type of engine won't be exceptional on a racetrack. The mechanism behind the critical cross-section is we want to use it as a nozzle and accelerate the air to increase the energy of the air column so its force overcomes any force that's trying to oppose the cylinder being filled. Like the end of the intake stroke, when the piston is coming up from bottom dead center before the intake valve closes, you want this column of air to keep filling the cylinder even though the cylinder pressure is rising. They also work as a one-way anti-reversion valve. Not many engines have their minimum cross-sectional area at the throat. If you look at multi-valves, usually there's more valve area than runner area. So your critical choke window ends up here. Or if you put large valves in old V8s, that usually puts the minimum cross-sectional area at the pushrod pinch. The designers wanted to keep their rockers straight, and that makes the pushrods come down either side of the port, so they have to squash the port to get around them. Some manifolds can move that minimum cross-sectional area even further up the runner. Either way, these minimum cross-sectional areas work the same, just they're less effective. Increasing velocity also increases the strength of the waves for wave tuning. Basically, as the port velocity goes up, it hits the closed valve harder, and that produces stronger waves, which makes more power. But also, as the velocity rises, the port losses increase, and this means there's a limit to the velocity you can use. Power will start dropping off at an RPM that produces a velocity of 700 feet per second. 700 feet per second is regarded when the port losses exceed the energy imparted by the velocity. So after this point, it's diminishing returns. There's also a phenomenon called sonic choke. If a localized area hits the speed of sound, it will speed limit the rest of the port. Like if a port is running at 500 feet per second and there's a localized hotspot at the speed of sound, the port will stall at 500 feet per second and not go higher. We try to achieve 700 feet per second in every port, but that doesn't mean the port will be happy at 700 feet per second. Straight ports will be happy at 700 feet per second, but ports that have to turn a lot or are very contorted will like a lower velocity. You'll probably make more torque with ports that turn something around 90 degrees with 500 or 550 feet per second. Next is the most critical area in porting, and it's called the short side radius. Depending on the port, this is the first place porters look at because it has the highest potential gains. You want a big slow turn with a large radius and a very tall floor, so air can get around it to this side of the valve. There's also a very high velocity profile across this short side, which you want to slow down, because air rushes down here and tries to cut the corner. And to combat that, we flatten and widen the floor. Basically, if you looked at a cross section anywhere through this turn from this direction, this area would be D-shaped. The D shape equalizes the velocity profile across that part of the port. The next area is the bowl, and that kind of does something similar to the short side radius. And the way the bowl works on this principle. An elbow has a lot of losses, generally over 10%. But if you have two pipes at 90 degrees, joined by an empty volume, there's only 1% loss, because the air has a chance to slow down and make the turn, because entry and exit losses are tiny compared to turn losses. And that's what we're doing with the bowl. So in porting, we balloon out this area depending on how sharp the turn is. Typical areas here for Pro Stock will be about 115 to 125% the throat area. Next we have is the port runner, and here we want to accelerate the air to the choke window, and we do that with port taper. You can't increase the port velocity quickly with a lot of runner taper because it wastes energy accelerating the air, so they use a shallow taper angle of about 4 degrees. Standard engines don't benefit much from runner taper. Next we have a radius entry. You don't want it too sharp or air entering from the side will overshoot and create a vena contractor in the middle, and you don't want too much radius or the pulses won't be sharply defined. You can see the radius here on this high-end sheet metal manifold. And if you look at the chamber, you'll see another radius on the exit. This usually only applies to 2-valve engines over 9,000 RPM. The way this works is a pipe with a radius entry will flow 146 CFM per square inch at a 28-inch H2O pressure drop. 146 CFM per square inch is the maximum flow as designated by Superflow flow benches, and is the number we use to calculate the discharge coefficient of an area. We can call this the radius entry to our manifold. But what if we added a radius exit? This area will now flow more than 146 CFM. I physically measured the flow on a flow bench, and in my case it flowed 152 CFM per square inch. And that's because the air exiting is controlled. Basically it doesn't go turbulent and start tumbling. So you could say this radius is acting like a diffuser. The controlled exit using a diffuser also increases the static air pressure. And lastly we have runner length. The distance from the runner entry along the center line to the valve seat tunes the RPM for the harmonic we want to use. Different length produces different delays for the returning pressure wave. Nobody uses the first harmonic because the runner length is too long to fit in an engine bay. The second harmonic is still pretty strong, but not used often because the distance between the second and third harmonic is so far that it leaves a massive dip in your power curve. From the third harmonic on, the waves get successively weaker. But it's these that are used because they're close together, i.e. less holes in the power delivery. These pulses can be in the order of PSI. Just look at this unremarkable BSA engine that shows 0.2 bar over atmospheric. You would assume high-end race motors to produce more than 3 PSI. Just on a side note, a Pro Stock motorcycle travelling at 200 mph will produce 2 PSI in the airbox due to ram air. As a word of caution, what works on a Pro Stock engine won't work on your standard engine. Just look at valve seats. Low-speed diesel has a 30-degree seat, high-speed diesel 40-degree seat, petrol has a 45-degree seat. If you want to rev an engine to 8,500 RPM, you need a 50-degree seat. 9,500 RPM, you need a 55-degree seat. And if you want to go 10,750 RPM of a Pro Stock, you need a 58-degree seat. You should now know what to look for in a port, so in part 2 we'll look at rotary ports and what characteristics they used.